and VIF analysis, AIC, BIC, all that stuff, that's the section going to be on. It's going to have an Excel portion and multiple choice like we had in the last exam. There's going to be 2 Excel problems. I'll even tell you what the problem types are because they shouldn't come as a shock. One is a QQ plot, which you know, like that's not shocking, we've been doing that. And the other one is VIF. The 2 main things we've been doing, those are, I'm not gonna put eigenvalue stuff on there because it's literally just copy and paste a matrix into MATLAB and tell it to do eigenvalues and eigenvectors. We're not gonna worry about that. So those are your 2 problems. So you know, you're gonna make sure you know how to do VIF, you should at this point, how to do QQ plots, you should at this point, be very comfortable with it. And then there's multiple choice related to interpreting QQ plots, understanding what AIC, BIC, VIF tell you, how dummy variables work, like the things that you've seen so far 1,000 times.
Would you like explain the concept of the
Oh yeah, so what VIF is doing is VIF is trying to determine whether your predictors, so what should be your independent variables, are truly independent. So what it does, remember VIF goes piecewise. So let's say I have four data sets. What I do is I say, we're gonna do a linear regression. We're gonna say, variable 1, instead of having, so let's just go through an example on the board. So that, I will say, if you follow the example you do on the board, the problem on the exam is going to be very straightforward because this is the algorithm of doing VIF. So we're going to be walking through it to make sure you're comfortable with it. So let's say you have a data set. You have Y, then you got a table of X1, X2, X3, X4. So you've got what should be your dependent variable, your 4 independent variables, right? And ordinarily, if you were doing regression, you would just regress Y versus your 4 X's, see what the regression analysis tells you, and you get your equation. But what VIF is doing is VIF is saying, are all these actually independent of each other or not? Because we've made an assumption, if we regress it with Y with these, that they're independent, and they may not be. So in VIF, what you do is you go, you know what, we're going to now treat this a little differently. I'm going to say this, I'm going to call X1 my dependent variable, then X2, X3, and X4 my independent variables. And I'm going to do a linear regression, where this is my new Y, these are my new X's, and I'm going to see what it gives me. And really, all you're worried about when you do this regression, you can look at the regression curve, the plots, all that if you want to, but really what you want to know is the R-squared value. Is you're going to get some R-squared value. And then you're just going to use that to calculate your VIF.
But we use adjusted R-squared, right?
Yeah, you use adjusted R-squared in that case, yeah. R-squared, but if you have more than one, you're going to use adjusted R-squared, just to be safe. And then I'm trying to remember your VIF equation, it's everything right. It should go to 1, so I think it's 1 minus 1 over R-squared, no.
No, it's 1 over,
It's
1 minus R squared.
1 over 1 minus R squared. Thank you. I was like, I was trying to remember the exact equation. Yeah, it says. Is that? Yeah, that's right. So what is this telling us? Well, what is our range for R squared?
0, 2.
It's basically 0 to 1, right? If this is 0, what happens to VIF? What's that? It's 1, right? So and I'm just going to put R squared instead of adjusted R squared, but no, I'm talking about adjusted R squared. If R squared is equal to 0, then VIF equals 1. What does an R squared of 0 tell you? What does that mean? If you see an R squared of 0, what does that tell you about your regression? What value do we want for R squared if we're trying to get a good regression? We want 1. 0 says it's utter garbage. It says that our X's do not predict the Y at all. In that case, that's good here. Because we're saying, do X2, X3, and X4 combined in some way predict X1? And R squared of 0 says it doesn't. So that means with a VIF of 1, Is VIF1 a good number or a bad number? It's good. That means, cool, I can trust that value. X1's reliable. Then we now shift and we say X2 becomes our dependent variable, X1, X3, and X4 are my independent. And we do it again. This is our Y, this is our X's, and we regress this. And we look for an R squared value. Now, let's say we get an R squared value, just for the sake of argument. Back over here. And let's say now we get an R squared equals 0.92. What does that tell us? It means it's a good model, but it also, if it were modeling it, it would be great. But what it tells us is that X2, which we want to be an independent variable, is not. It's actually predicted by basically 92% of its variation is predicted by X1, 3, and 4. That tells us there's something wrong here. And if we do the VIF calculation on that, and R squared equals 0.92, that's 1 over 1 minus 0.92, that's 1 over 0.08, that's greater than 10. I don't know the exact number, because I can't do that in my head. It's 100 over, actually, I can do that in my head, and this is sad. That's 100 divided by 8, that's gonna be 12.5. I'm not some savant. That's basically a 1/8, and 1/8 is 12 and a half. So it's just 0.125 times 100. So I just had to shift the decimals. I like doing math in my head, but that's another illness that I need to deal with. So if we see a 12.5, is that a good number or a bad number? That's bad. Why? What's that threshold we're really worried about? Over 10. If VIF is over 10, wait, that means that for VIF over 10, that means your R squared has to be 0.9 or above to get to a VIF over 10. That means that 90% of your variation in this, what you believe to be independent variable, is actually predicted by the other independent variables. That means it's not independent anymore. It's actually some sort of function of these three guys, which is why we want to get rid of it. Because we want to use only independent variables if we can. Does that make sense to everybody?
What it means it's, say again, you mean it, if the VIF is over 10, it means it's correlated to the other independent.
Exactly. We have what's called multi-collinearity. It is now linear with, because remember, this regression is just a linear analysis, right? It's the, are you linear with this? And so it's saying, is this guy linear with these three variables? And this says, yeah, 92% is linear by some combination of these. It could be to one variable, it could be a combination of all the variables of some sort, but it's saying this has a linear relationship to these variables combined. And that, yes ma'am?
So in this case, our R squared value being closer to 0 is a good thing?
Exactly. With this one, you don't want R squared values that are high. Because if they're high is great if you're regressing a model. High is terrible if you're trying to prove these are independent. Because if they're not independent, that R squared goes up. And so then we do the next one. We go X3 and X1, X2, X4. We do the same analysis. Then we finally do X4 and X1, X2, X3. Oops. So these are your X's, this is your new Y. And you just do this analysis on all these, and you calculate the VIF for, and what this VIF applies to is, what is the Y variable? This VIF links back to that Y variable. So every time you do this, the VIF is for the one that you're calling the Y. And it assigns a value to that one. So then you get a table of all your VIFs, and then you make a decision. So let's say I give you, you find this out and you go, okay, variable, and then VIF value, and we go, our variables are X1, X2, X3, and X4. Why am I not doing the Y here? Why am I just doing my X's?
Because you want to check whether your variable is linear.
Exactly. This has nothing to do with the actual regression itself. This is just looking at my independent variables and saying, are they independent or not? It's not making any claims as to how the Y relates to them at all, because this is just cleaning up before we start the regression, because if we introduce all the variables and some of them are nonlinear, we end up double counting a variable functionally. and it's all of a sudden this thing that we think is a linear relationship isn't. And it's because by changing x4, we're changing, like if we find out that there's a strong relationship between x4 and x2, that would be if x4 changes, x2 changes with it in a way that's predictable. It's now no longer a change in x2, but it ends up being picked up as an independent change in x2. So it allows us to eliminate those relationships. So I get a VIF, and I get my VIF for one is 1.5, for this one is 12.3, for this one is 4.7, and for this one is 2.3. Okay, so let's say I get these values. What am I worried, on X1, am I worried about it? No, why am I not worried about this? It's not even less than 10, it's less than 5. So, kind of rule of thumbs are, if you think about it from the R-squared perspective, greater than 10 means that 90% of the variation of that variable can be predicted by the other variables. Does that make sense? Because your R-squared is basically 0.9 when you have a VIF of 10 or above. It's 0.9 or higher. That means that X, like, that, so let's say, so this one is, let's say 1.5. So that means that our 1 minus R squared is 1.5. So that would be, let's see, 1.5 equals 1 over 1 minus R squared. That's 1.5, whoops, I gotta do it too. 1.5 minus 1.5 R squared equals 1. Negative 1.5 R squared equals negative 0.5. So R squared is equal to 0.33. So for this 1.5, that means that our R squared was 0.33. That means that a third of the variation in X1 was predicted by these guys. The other 2/3 is just happening on its own. That's great. That means that variable is basically 2/3 independent, is what that tells us. That's a good number. We're happy with that. Does that make sense? Everyone comfortable with that? It's kind of like the same thing with weight and height. With weight versus height, there's a portion of the weight that change that is predicted as you get taller, and then a portion that's independent of whatever you are as a person, your body structure, all that. It's kind of taking that. It's understanding that there's two pieces to it. Now, the second one is 12.3. So this one, good, keep it. 12.3, what about this one? What are we gonna do with it? We really wanna toss it, right? Why? It's above 10, and that 10 means, remember, if R squared was 0.9, then VIF is 10, so that means R squared has to be bigger than 0.9. Like 0.92, 0.93, something like that. That means that 93% of the variation in that independent variable is predicted by the other three variables. So that means X2, if it moves, 93% of its movement would be predicted, let's say it's 92, 93%, is predicted by, sorry, X1, X3, and X4 in some combination. That means it's no longer independent. It's a function of those other three variables. At least 93% of it is a function of the variables. Then there's like 0.7%, or there's 7% that you go, well, yeah, but there's some variation. Yeah, but is it a good value? I wouldn't trust it at that point. So I'd toss it. Does that make sense? Now, 4.7. Kind of wish-washy, right? It's not above 5, but it's approaching 5 where we go, we should probably check it. We should probably keep an eye on it. So what I would do on that one is I'd probably keep it, but monitor it. And what I mean by that is this. At a VIF of 5, what does that mean for our R squared? So if you go 5 equals 1 over 1 minus R squared, that's 5 minus 5R squared equals 1. That's 5R squared equals negative 5R squared equals negative 4. R squared equals 0.8. So even at 5, we still have 80% of the variability predicted by the other variables. But that's a threshold that normally when you do this, you go, it's not great, but still 20% of it is reliable as independent. So you'll still do it, but what you're gonna do is you're gonna say, if I start taking other variables out, I may check it again once I remove this variable. So what will hopefully happen is I remove this one, and I do the analysis with just X3 and X1 and X4, and I find out, oh, this dropped from 4.7 to like 2 point something. And I go, okay, its relationship was to this variable very strong. by eliminating that one, I've actually cleaned this one up quite a bit too. Does that make sense? Because you basically are eliminating possible collinearities when you do that.
Could you say it again, please?
So the idea is, remember, what we're looking for here is there a linear relationship between your independent variables? So let's say I have these two in here like this. This one I'm saying toss it, 93%. This one, it's about 78% roughly. But it's below 5, and our rule is if it's below 5, if it's near 5 or below 5, we generally are okay with it. But if it starts getting close to 5 and a little above 5, between 5 and 10, we start to get really iffy with it. So we're gonna monitor it, and what we're gonna do is as we process our data, we're gonna see if there's anything we can throw out. And if we throw out something like this, we're gonna go, okay, how does that affect the other ones? And very likely, if you throw out something that has a high collinearity like this, the other collinearities are gonna drop. Because they were linked to something. And they're likely linked to this guy that has a really high collinearity. Because he has to be collinear to something else. This is an independent behavior, right? It's the, how are you related to these other variables? If I eliminate it, I probably eliminate a lot of this high here. And when I eliminate this guy may drop to like 2.1 or 1 point something. And then we do that, we go, cool, I've actually cleaned up my data across the board by doing that. And we never did that exercise, but that'll be a good one to do after the exam. I'm not gonna make you do it on the exam. When you remove it, how does it affect the other ones? And you're gonna find that eliminating a highly collinear variable will often make the other variables look much better. Because they're linked to it, and that it's basically picking up all the links in one place and coalescing them. And that's why you see these others not being all that high, but then this will be massively high. It's the primary link between all of them. So we do that, this one then drops potentially. And then of course 2.3, is it more than this one? Yeah, but it's still good. And you all have found that with some of the data you've looked at. A lot of you have said, my VIFs are all coming back like 1.0 something, 1 point. Yeah, that's ideal. That means they're truly independent variables. That means they were collected in a logical way, that they actually collected independent data. And if it's a well-designed experiment, you should have VIFs that are much closer to 1. Like literally 1 point something. And a lot of times it'll be like 1.02, and that 0.02 isn't even real. It's just there's anomalies in the data that give the illusion of some tiny, tiny, tiny link. Does this make sense? This is purely cleaning up your independent variables to make sure that what you're regressing is a multilinear problem and doesn't have collinearity. Collinearity is where two variables move in conjunction in the same direction at the same time. There's a clear relationship between them. Yes, ma'am.
So when we're done with the DIF and we've said, okay, you know, if there's one that's obvious, like, okay, we should probably test this out,
Yeah.
do we do another regression just
You-
without that?
We'll do that after the exam, because that's actually the kind of the next step is let's see how it looks after I get rid of that one. Because you want to eliminate, what may happen, I mean, God forbid this happens, is you eliminate this guy, and all of a sudden this one goes down to like 1.0 something, this one goes to like 1.0 something, and this one goes up a little. And it's like, oh, you're a problem with these two. So then we might get rid of that one too. But likely that's not gonna happen. When you have one that's that far off, normally getting rid of that one, all the others are at a drop. But yes, when we're doing the true data analysis, we will do that. We did the first step, which is analyze it and look for any. If you don't find any, then you're good. If you find that, you toss it and you do it again just to verify, without that one being in there. Yes, sir.
Could we look at like some Excel, like review like the Excel files that everyone knows?
Yeah, what do you wanna look at?
The VIF and QQ slides?
Yeah, anybody everyone good with this, or? Okay, cool. Yeah, let's do that. Okay, as we're putting this down, and we know QQ plots are gonna be on there, what is a QQ plot? What's it doing?
Data to the one.
You're doing good there. You're so close. You're comparing your Y data, the actual dependent variable, to a normal distribution. Why?
To check your vision. No more or not.
Right. Why do we care? Because most regressions rely on the data being normally distributed. Almost every regression technique wants the data to be normally distributed. If it's not normally distributed, your regression is going to struggle and possibly not even predict it well. So ideally, we want our data to be a normal distribution. And QQplot does, QQplot will actually help identify, is it normal? And if it's not, then we have to address that. We'll talk about that.
Was it the dependent variable?
What's that?
The dependent.
The dependent variable, yeah. So QQplots only have to do with the dependent variable. They have no, so like VIF is only the independent, QPlots are only the dependent. So you're looking at cleaning up the two pieces independently. Why do you want to do that? Well, the primary reason you want to do that is because you want your data to be truly independent. If I clean up my Y using X or my X using Y, I'm now creating a link between them by how I'm analyzing them. I don't want to develop that link until I'm doing my actual regression. Because if I analyze my X data with respect to Y and my Y data with respect to X before I do my regression, I'm going to create links there by how I manipulate the data. So we want to manipulate them independent of each other so we don't have those issues fighting each other. Does that make sense? It's a weird concept, but everything you're doing is literally getting stuff as clean as possible to start with so that you have something moving forward. That'll work. Let's see. What data set was that? The QQplots?
It's
There's a March 31st.
March 31st? Hopefully I saved it. I think I did. And we'll just talk about like, what does that technique look like? What does it represent? That way, because not shockingly, you know I have no problem telling you you're gonna do QQplots because yes, that's one of the primary things you've been doing. So of course you're gonna be doing that on the exam. I don't even feel like I'm giving anything away there. So, as soon as this loads. Okay, let's go over here. And eventually this will come out. Wait, right. Oh, cool. Okay, so you should have this data set where you have a set of Ys and 5 X's. Right? So with QQplot, what we want to know is that Y data, is it distributed normally? And so, and actually let's go back to this data set here, because this is what we did the QQplot from. You have a bunch of data sets, right? And these are already ordered, unfortunately. So let me do this. I'm about to, what I'm doing does not have anything to do with what you're going to be doing. This is just so I can create disordered data. Let's do 1 and 1 million. There's a logic behind what I'm doing here. Bear with me. I'm reordering one of these data sets to be random order. So I'm giving it a key to go off of. And then I take this data set. Oops. This one. Sort. Custom. Fine. Okay. It's gonna be that way. That is good. Over here. Now you'll do it. One, nope, the other one, on the smallest to largest. Okay. There. Now we'll delete this. So what I've done is I've created this random data set 1, right? And it's the data set 1 you have uses, but what I've done is I've just reordered it because we want to go through it stepwise. So QQ plot, and you can see what happened here when I reordered it. Does that tell us anything? That's a shotgun blast. Why? Because it's now random ordered. It doesn't tell us anything. So if we look at that, we're like, oh, that really doesn't help. What we want to know is that data set distributed in a normal manner? And we do that by comparing it to a normally distributed piece of data. So first thing we have to do is we're going to create a rank order down the left side. And this is literally just 1, 2, 3, 4. Like basically you're just numbering all the way to the bottom. In this case, I think it's 100. Yeah. And we're assigning a number to each one of these values. Does that number mean anything? No, absolutely nothing. That's going to become important in a second. The next step you want to do is, okay, I now want to order my data set such that I have the smallest at the top and the biggest at the bottom. So you're going to pick your data set. I unordered it so we could do this. I then go, okay, sort, smallest to largest. Don't expand it, just leave everything else alone. Keep that first column the same. And say sort, and it does that. Now we've sorted our data. Now we have to make our normal distribution to compare it to. Because this data set still doesn't tell us by itself whether it's normal or not. It just says we've got it in order from smallest to largest. Why am I ordering it from smallest to largest? If I look at a normal distribution of data, what does it look like? It's a bell curve. And what does that bell curve represent?
I'll spread out the range of possibilities.
Exactly. It's basically how often do you see an observation in this value range? So it's like, so at the very small numbers, I don't expect a lot because it's the area under that bell curve is very small, right? Because remember, a bell curve looks like this and goes like that. And it's basically like how many observations, that represents how many times you expect to see a value in that area. And so, very, very small numbers, I expect to be very small. I don't expect to see a lot. Very large numbers, I don't expect to see a lot. I expect to see a whole bunch in the middle. And the closer I get to the median value of my range, I expect to see more. That's what it means to be normally distributed. Most of your data is grouped around the average, and then it gets less and less as you go out. Same thing with like average male height. I think average male height in the U.S. is 5'10", I think. We expect to see more people more men at 5'10". We don't expect to see many over 7 foot. They're in the NBA, the bulk of them. I mean, realistically. And then the other side, like 4 foot and under, they're on shows on TLC or Bravo. We see them there. But in the middle, people that are my height, we don't have special skills being 5'10". That's not a skill set. It's just being 5'10". I'm technically 5'10" and 3/4. I only know I'm 3/4 because I dated a girl in high school who was 5'11", and she reminded me that she was a quarter inch taller than me all the time. That didn't damage me at all. So that's what we're looking for, is it should look like this. If we count the number of observations in certain windows, we should see a lot more around the mean. We should see, like, if we have 100, we would expect like 10 in this window, maybe 8 in this window, another 6 here, like 2 here, and then maybe 1 out here at the end. Like, that's how we would expect the number of like times we see those numbers show up. Does that make sense? Think histogram. This is basically just a curve shape, a curve representation of a histogram. You don't know what a histogram is? Anybody not know what a histogram is? Please ask if you don't know. It's basically counting how many times something happens. That's all it is. It doesn't actually look at the values don't matter other than they fall in a category. And so a bell curve just represents a normal distribution of a histogram. So that's what we want to know. We put them in order so we can see how many teeny tiny values we have, how many big values we have, and how many we have in the middle. And we're looking for that distribution. But to know whether it's normal, we need to compare it to a normal distribution. We don't have a choice. It just is what it is. So what we do is we create a normal distribution to compare it against. And that's what this equation right here does. Is it says, okay, give me a normal for a sample, and we want the inverse. So we want what the actual value should be if it falls in the low end of the distribution. And it says, okay, what am I basing that on? I'm basing it on the percent, which is this, the number, over 101. What is that? That's about 1%. So it's like, what do we expect the smallest 1% to be? So basically, what do these guys look like? What number would I expect that to be? And that's what it's doing. But it's basing it on just some normal distribution. It doesn't matter what the values are, it just matters that how they compare to each other. And then at the next one it goes, okay, if that's 2, then that's roughly 2%. What do I expect the number to be? And then 3%. And so it's basically creating what that distribution should look like. Does that make sense? Everyone comfortable with that? And it does it in order, because at the bottom we get to 101. If you look at the 101, we're at 2.33 versus negative 2.33. Split perfectly on 0. One on each side. And then it goes up. Basically, allows us to basically space the points out. And if you'll notice, it goes negative 2.33, so then it goes up by 0.18 roughly. Then it goes up by about 0.17, then about 0.13. You'll see every time it goes up a little bit less. Why? The data points are getting closer and closer together in the middle. Because we expect more data points in the middle, so they would be clustered more. So that's what we're seeing, is that clustering of the data as you get closer to the middle values. We then compare that to our data. Does our data in the middle values of it, cluster together or not? And you can even see it in the shape of the curve here. These points right here are spaced out. These are clustered together, much tighter squeezed, right? If they are shaped right, you get something that looks like this. It falls perfectly on that 45-degree line. A bunch of data points squished in the middle and a few spaced out along the edge, but they still follow a straight line, as you can see happening right here. But what's happening on this guy? It's curving downward, right? This at the bottom, it still comes back to the line, so you really can't, it's not curving away from the line, right? If anything, it's kind of curving toward the line. So this is fine, but up here, you can see it turned away from our data set. Everyone see that? This is a downward curve. What does a downward curve represent? According to our notes. It's left skewed, right? Because you have you have 4 possibilities, right? You have left skewed, right skewed, normal, and heavy tails. Those are your options. So this is left skewed because it's curving away. This is normal. This is right skewed because you can see it's curving, like there's a downward, it's basically a downward activity, it's curving up. This is heavy tail because it's perfectly linear in this region, and then you have these big ugly guys at the end that are just throwing everything off. Those are the triggers to know what's happening. Does that make sense? Do you understand how to make the QQ plot? QQ plot, if you don't remember, is just this function, and then whatever number it is in the sequence of the ordered data, so like 1, 2, 3, 4, so forth, divided by the number of points plus 1. We do plus 1 because if you don't do plus 1, you get the normal distribution of 100 over 100, which doesn't exist. Why doesn't it exist? Because you never get to 100% of your distribution. It approaches it approaches down here, but it never crosses this line, so you can actually never get to 100%. Same thing if you had a 0, it would give us a odd number also, because it'd be like, that doesn't exist. You can never get to the 0 point in your data or the 100 point. Yep.
You said left skewed, heavy tails, right skewed, and what was the last one?
Heavy tail. Left skewed, oh, you said heavy tail? Sorry, normal. You also have normal distribution. Normal distribution is, it falls perfectly on the line and everybody's happy, like this guy. Okay, so we've determined this guy is left skewed. What do we do? What is it? You have a couple options, right?
Exponent squared.
Is it squared in the exponent or is it natural log and square root? I forget which one is squared. Okay, so what it's telling you is it's left skewed. You have more data at the small end than the large end. So we're going to try to shift this data and determine the shape of it. So, and where this comes from is this right here.
ordered it as one against the little thing.
Somebody in Excel, just because we're bored, take that data table, the 1 to 100, take the square root of it and plot it. Versus, let's just plot it to see what shape it takes. Yes.
So like
You said if it's left skewed, we're gonna
click that little filter. on
You're
that
gonna,
side.
well, we're gonna talk about that, but
Click
it's,
the filter on the side.
we're going to either
No, no,
do,
no. Go to the
if it's left skewed, we have to do
filter.
squared or
Third option,
exponential,
no.
right?
That one.
Just for left skewed. For right skewed, you do
Select
the
that
inverse of
one.
that, natural log or
All
square
the way
root.
to the bottom. So like that. Okay, data set. And then that's what I did.
Yeah, just to see what it looks like.
We have the exact same values.
Yeah, just plot that. Actually, I can do it. Here, take a picture.
It
Just so
must
you
be my
guys know what
labels. I
I'm
bet
talking
it's my
about.
labels. There's select.
So just because I want to know what this looks like, so I can give you a demonstration. Let's see, we're gonna do the square root of this column
I bet yours is my better.
of that number. And it's gonna be, this is a worthless number, I just want you to see this so you understand why we're doing this. SQRT of this guy. Except I put a question mark in there for some stupid reason. There we go. And then I'm gonna say insert plot. What do you notice here? What's it doing? It's curving up and flattening out, right? That's a log curve.
There.
You've seen log curves before, right? They go up and approach a value, but they never get there. Or, so this is what upward data looks like. This is what that data set 1 looks like, right? If you compare them side by side, oops, except I moved the wrong one. Come on. There we go. You can see you have that same idea. This curve here, this kind of curves up here. This is where the idea of how to correct it comes from. It's like, oh, if I see that shape, what did I do here? Well, I took the square root, so how do I overcome that? I square it. So I can square my data, and it'll fix a curve like that. If I did an exponential, I'll show you, you'll see the same kind of thing. Or the natural log, not exponential. So I do equals natural log of this. What do you know? That same type of curve, right? Well, how do I correct that? I take the exponential of it. It's taking a shape that we know when it looks non-normal, and that is exponential and square root are not normal distributions, and it says, how do I fix it? Well, here's an example of, this is demonstrating exactly how you fix it. By creating a bad data set and say, oh, if I see something curved that way, how do I undo what I did? So if I have the natural log, I undo it by taking the exponential of that number, and it fixes it. Does that make sense? That's where this comes from, is it says, I know this shape, how do I fix it? Now, what you're gonna notice, this is more extreme than this. In reality, this is gonna happen a lot where it's not as extreme, but it'll still help flatten it out some. And if we go over and look at our transformed Q plot for data set 1, what did we do here? Well, we squared it. And we found it's a little better. It's not great, but at least it's a little bit better. And that's our goal there, is to get it closer to normal. And why does it not work perfectly? Because none of your data is ever perfectly squared or perfectly natural. Yes?
What does it mean for our data whenever, for example, we had left skewed, right skewed, we had all sorts of.
Oh, what does it represent?
Right, and for example, we tried exponential, we tried squared, nothing worked but heavy tails. So we had to treat every single left skewed, right skewed, heavy tails as heavy tail. Or I guess, I don't know, we had to like just take out values from the top and bottom.
That just means that you have outlier data at the extremes that are gonna happen.
Yeah.
And when that happens, and this is something I'm glad you brought this up. You're often gonna have a combination of things happening. It's very possible to have a section of your data that is left skewed, a section of your data that is right skewed, and have heavy tails. Because real world data doesn't follow all these simple rules. So what you do is you just do the best you can with it. What you're talking about is, ordinarily what you would do is say, okay, I'm gonna treat it as it has heavy tails, and it is either left skewed or right skewed. So let me take out the heavy tails, see what I have now, and then see if I can fix that middle piece.
Yeah.
And you kind of accept that the edges of your data, you can very seldom represent well.
Yeah.
And this is what you're gonna find when you do regression and you do model development in industry, is your model's gonna be really good in the middle and suck at the edges. There's no other way to put it. And so you can even see with this one, if I treated this as a very heavy-tailed model, and I said, well, if I cut it here and here, now it's actually linear. But what I've had to do is I've had to limit, so my goal is to try to reshape the Y to get it normal, and if I can't, I have to then trim it and say, this is where my model fits. And when you trim your data down, you're saying, I'm limiting the scope of my model. It'll only work in this range. Above and below that, it just sucks. And you've dealt with that in all your classes where it's like, this Antoine constants are good for this temperature range. That's what they've done, is they've figured out where that model fits, and the rest of the places you go, oh, you need new parameters. Let's fit new parameters. And so that's what you may have to do, and we'll talk about that as we progress in the class.
Is it valid to like combine methods? So for example, could we use an exponential and then trim the edges if we find that we can create a better fit than one? Okay.
Yeah, all you do is you're taking the exponential and then trimming
And then
it
trimming.
and limiting the effectiveness of your model in a certain range. And that's perfectly valid. Yeah, because this is the issue with real world data is you're always gonna have things that will not work. At the edges of your model, you're just gonna have failures. And when that happens, you trim it and say, I trust my model in this range, I do not trust it beyond those. And like I said, you dealt with the Antoine equation as a great example because it gives you different sets of constants based on the temperature ranges you're working in. They regressed a certain range and said, it works here. And they said, but for this range of temperatures, you have to use these. And for this range of temperatures, you need to use these. And they often overlap a little. And what that means is that at that interface, you can use one or the other, and they should both be relatively close. And that's called a piecewise regression, is it's saying, I can create a model for, like, find a data set that's this long. I can say, I can create one model that fits here, one that fits here, one that fits here, one that fits here. All four are different, but they work. And then you do what's called piecewise regression, which is when I want to make a prediction, I pick my X value and go, okay, where does that put me on here? It's here, so I use this model. If it falls here, you can use either, or use both and take the average, like you have options. This is the reality. I would love to be saying you're gonna be able to fit a model to the entire spectrum of your data. That is never gonna happen. You're gonna say, I have a model that works really well here. If you want a model that works well here, I gotta make a new one. And they are likely not gonna overlap, or if you might get them to overlap at the interface. And that's your goal, is to get models that overlap a little bit so that you have a smooth transition between one model to the next, so you don't have anything weird happening. And you may even do, to help create smoothing, do a weighted average between them. That as you get closer to the end of this one, this model has less weight than this one. As you get closer to the model this model has more weight than this one. So you do things to help smooth your model out and make it fit better. We'll talk about that after the exam. But just know, if you have to do manipulations like that, it's perfectly valid to say, I may have to do two things. And if I'm doing a like natural log or square root or squaring or an exponential, I can use all my data. But I may still do that and go, I still have these heavy tails that I have to do something with. And you just cut them and say, my model's good in this range. And everything, all the data out there, I just can't predict. Yes.
So then that's like the data set one transform that we were going to like try to find.
Where we did the square. Yeah. So heavy tail versus light tail, what's causing is you have more data on, like, basically instead of being a normal distribution like this, instead of having this guy, you have something that kind of looks like this. Where that peak is now skewed slightly off. Or it could be the other direction where it's skewed like that. So what you're doing is you're taking that skew and you're trying to pull it back to the middle. So that you have that normal, and taking the square root or square of it, depending, or natural log or exponential does that. Because if you look at this exponential right here, notice that if you do a count of this, I'm trying to see what the number is. It gets slower and slower and slower as you go up. It moves faster at the bottom. It gets slower as you go up. You actually have more data on the right side than you do on the left side. So that's where the left skew concept comes from. Right skew, you have more data on the left side than the right side, so it creates it skews your tail, makes the tails longer on one side or the other. And that's what you're seeing. So you're trying to shift and pull that back to center and make those tails rather symmetric. And that's all you're doing when you do that manipulation of your Y data. Does that make sense? So the key with this on the QQ plot is you're only dealing with the Y, you're not touching the X's. you are then doing it, comparing it to a normal distribution. So you first have to order your Y data from smallest to largest. You then just number it, 1 to whatever, and then you create your normal distribution based on that where it is, like what number is it in the sequence. Not its value, but where is it on the list. And then you just plot that data versus that normal and see what does it look like, what's its shape. And then if you have a certain shape, how do you correct it? And you're gonna correct it with the tools you know, which are exponential or squaring, or exponential or squaring, or logarithm, or natural log, or square root. That's pretty much your options. You could even do second order, like you could square it, you could do raise it to the 4th power, raise it to the 6th power, any even number power, because it's just gonna make that curve. So, depending on how extremely curved it is, if it's curved pretty aggressively like this, I would say you're gonna do natural log. Yeah, natural log, or you're going to do, or you're gonna do like raised to the 1/2 power, 1/4 power. Like, the higher I make that power, the more aggressive the turn is. And it starts turning harder and harder. So depending on how hard the turn is, you may try higher orders. Don't worry about that for the exam, we'll talk about that after the exam. Just know that there are ways to imply or to impart more or less shape to the curve. You do that. Okay? Yes, sir.
So in terms of the Excel portion of the exam, it's gonna be QQ, plots, and
And
VI.
yeah. Because that's really all I can text you all on Excel. Okay, everyone comfortable with this? And then the multiple choice are gonna be like what you would expect. Like, how do you know if an AIC 2Q models is better or worse? How do you know if BIC is better or worse? How you interpret DIF? What are your thresholds? If I see a certain shape, what does it mean? Is it left skewed, right skewed, normal, heavy tail? Yes.
How many multiple choices do you know?
There are 16 multiple choice. There are 3 matching that are 4 pieces each. I literally have it all built. Like I can tell you, 16 multiple choice, 4 matching that have 4 things you have to match on each one, and then 2 Excel problems. They are worth 2 points per blank on the multiple choice and on the matching, and 22 points per Excel sheet.
Dr. Henry, we need more time.
3 matching.
That's crazy work.
So there's 16 and then 12 blanks that can be filled in on the 3 matching. So that's 28 blanks. So that's 56 points at 2 points per. That leaves you 44 points for your Excel. 22 on each one. Like I literally have the whole thing built. I know it by heart. Yeah. Let me have that information. Well, and here's what I'm gonna say, because the question was asked about AIC and BIC. The key to remember with AIC and BIC is that they are comparing 2 models. Okay, so this is, I've done my VIF, I've done my QQ plots, and I've now regressed my data, and I'm gonna compare which model's better than the other. The thing to remember about AIC and BIC are this: lower number is better. The lower the number, the better the model is. So if you're comparing 2 models, you calculate their AIC, you're not gonna have to do it on the exam, you don't even have to have the equation. Just know the behaviors. And it's a smaller AIC number is better, a smaller BIC number is better. Now, what's the difference between AIC and BIC? Do you remember how they differ?
The VIC penalizes predictors more than
Yeah, BIC penalizes additional predictors more than AIC does. So I recommend using BIC given the choice, because what it does, it says, yeah, this model's good, but you had to use a lot more stuff to get there. So we're gonna give you a little bit of a penalty on top of that. So BIC, if the more predictors you have, BIC penalizes you more for those. That's the difference between them. Other than that, they do the same thing. They're comparing 2 models, lower numbers better. Okay. Any other questions? Yes, ma'am.
For TSS, so you said for RSS is unpredicted variation.
Oh yeah, I'm gonna ask you that, no worries. But you know, we'll talk about that after the exam. I don't want to clutter your brains with a thing that you don't need to remember for the exam. That's a statistical thing, which is useful to know, the RSS versus SSR and TSS, yeah. It has to do with variability in your model. RSS is predicted variability in your model. SSR is unpredicted variability in your model, and TSS is total variability in your model. But we'll talk about that in more detail after. Any questions? Yes, sir.
Is everything gonna be in Blackboard?
Yep, everything will be in Blackboard. The Excel files will be, when you open the exam, you can pull them down, work on it, and upload it back. All the data's in there. I would recommend, I know it feels like a long exam. I promise it's not that long. I promise. But what I would say
I'm gonna
is,
be where I'm looking.
what I would say is, get your multiple choice, get your QQ plot done, then do VIF labs. Because that is the longest of the, by far, of the Excel files. But it's the same weight as the QQ plots. I do the QQ first, because
Got it.
but I mean,
Noting it down.
in reality, the QQ plot is one QQ plot analysis. So that one's relatively straightforward to do. The VIF is multiple X's, you have to do it piecewise, there's no way around it. So give yourself, get through, if you do all but the VIF and you don't get that, that's 70% of the exam already done, and you'll get those done relatively quickly. And that'll give you time to VIF, and then whatever you get to in the VIF, once time is due, you'll submit it. I do curve the grade to the highest score, so if nobody gets done with that problem and the best somebody gets is halfway through it, that's 11 points off. That's 11 points everybody's gonna get.
Nobody did the VIF.
If nobody has the VIF, if that's what I'm gonna question. Because that's just like collision at that point.
Do you want me to nobody wants to? I'm so serious. If we don't get 11 points, I know somebody, one of y'all.
Yeah, here's the thing, it only takes one of you doing it to screw the rest of the class.
Seriously,
So,
if one of y'all
do you trust everybody in it?
y'all be playing.
And I like you guys, I would not trust you to not do it. I mean, I could have the entire, all the groups in my budget, and I wouldn't trust them to not do it. One of them would undercut. Yes. Sure.
Don't get him, you to do it. You're gonna do that problem, huh? I can barely come to class, what you mean?
She was gonna do the problem.